Okay, so we're on day 2 of scientific notation, chapter 8.4, and we're just trying a few more problems in your notes so that you are strong with this. So what happens when we multiply these first two together? What do we do here? Zach? This is just a string of factors, right? So we said on Friday that we could multiply those kind of like factors next to each other using which property? Remember the name? What property allows us to move factors when you have a string of multiplication? Everyone say it? Commutative. You can commute things around, right? So we could put 7.3 next to 5.8, and then we could put the powers of 10, negative 5, and 10 squared next to each other. Treat them separately, right? And so, did you do this? What do you get when you multiply those two? Who has it? 7.3 times 5.8. Just that. I want to know just that. Jimmy? 42.34. Who agrees? 42.34? Okay. And then we're going to write, again, our answer should be in scientific notation. And so when we multiply 10 to the negative 5th times 10 to the 2nd, what do we do with the exponents? And we get 10 to the negative 3. We add those exponents. And so is this the correct answer?
No.
Good job. So it's not because it's not really scientific notation. It looks like scientific notation. But what's wrong with it, Sarah? Right, this decimal, this number 42 is not scientific notation, right? We need a number between 1 and 10, a single digit number. So we're going to move that decimal one place to the left. We're taking away a decimal place, so what will we do? We'll add it back. Here, we add it back because we took it away over here. We end up with 4.234 times 10 to the negative second. Okay? So we kind of treat the parts, the factors, we kind of separate and treat them a little differently. If they're powers of 10, they're easy to multiply together, and we do that separately than the other factors. So in this case, tell me what you're going to multiply together, Casey.
8.1 times 9.
Times 9. And then we'll multiply 10 to the negative 4th times 10 to the negative 6th. So when you get, what do you get with 8.1 times 9? 72.9. And then the powers of 10 give us 10 to the negative 10. Good. And so when we take away this decimal place, we'll have to add it back, and what do we get? Times 10 to the negative 9. Thumbs up if you got it. Any questions? Okay, again, we're just reviewing again. Try these two division expressions and write your answer in scientific notation. So what do you get when you, well actually, before I say that, again, these are all factors, right? So we can simplify the factors that have common factors. So what do you know about 4.1 and 8.2? What do you know about those, Brian? It's half. So if we were to simplify that fraction, 4.1 over 8.2, it equals 1 over 2, or give me the decimal equivalent, 0.5. So we could write this part here as 0.5, right? Times, and now when we're dividing powers of 10, what do we do, Ryan? We subtract. So from the top one, we could subtract the bottom 8, and we end up with negative 4. Good. And so is this scientific notation?
No.
No, because that number, this is representing C, right? Is not a number between 1 and 10 in the ones place. That's a 0. So we're going to have to move the decimal which direction? To the right. We're adding place value, so don't forget to take it away, right? We added one place value, and so, Ryan, what do we get? 10 to the negative 5th. Good job. Okay, how about the second one? 6 over 8. Can someone give us the decimal equivalent of 6 over 8? What is that, Christina? Nope. She was going to use her calculator. And you know what 6 over 8 is. Divide them both by 2. And what do you get?
2 over 3.
6 divided by 2.
Okay.
3 over 4. 3/4. What is that? 3/4 of a dollar. What is that? 0.75. See, you can do that. 0.75 times 10. And again, we're dividing these powers of 10. So 10 to the negative 3 over 10 to the negative 6. What would you get there, Christina?
10 to the negative 9.
You have to subtract that lower exponent, right? It's a negative exponent, though. So when you subtract negative 6, you're really adding it. So negative 3 plus 6 is a third. And is that scientific notation? No? Good. So which way will you move the decimal?
To the right.
One place. We're making it larger by one place, so don't forget to take it away. And can you say the expression now?
7.5 times 10 to the second.
To the second. Okay? Very good. Questions? Questioning. This part right here, 10 to the negative 6 over 10 to, 10 to the negative third over 10 to the negative 6. If you think about it, if we weren't writing in scientific notation, we're not to leave an expression with a negative exponent, right? And so, what does a negative exponent do, Jimena? It tells you to move that term where? Well, what if it's in the denominator? Like this one down here, 10 to the negative 6. Where would we move that term? The numerator. So it tells you that you need to move that entire term to the inverse location. Okay? So this whole thing could be, how could you write that fraction with positive exponents? What would it look like? This one equals 10 to the what? When you move it, okay, when you move the negative, this one to the numerator, you lose the negative, okay? But you keep the number of tens. So how many 10 factors are moving up? 6. And then how many are moving down?
3.
So you could write this expression this way, right? And then you can imagine now writing the tens that many times, right? We literally could write how many tens in the numerator?
6.
So we would write 1, 2, 3, 4, 5, 6. And how many in the denominator?
3.
1, 2, 3. Good. And so 10 over 10 is 1. 10 over 10 is 1. 10 over 10 is 1. And how many are left? 3. And that's what we got, right? We said we had 10 to the third. And we did it by using the property of subtracting the exponent that was in the denominator from the numerator. We did it that way because this is a lot of work to show and we want to get there quicker. But that's the reason why. Okay? Okay. Let's try a couple more, raising some scientific notation to a power. Okay, so when we have a scientifically notated expression, this is a scientific notation, raised to the third power, what does it do, Nico?
You distribute the 3.
It feels like you're distributing the 3. So 5 is happening how many times? 3. So it's like we have 5 to the third times
10
to the
negative 24.
negative 24. So he actually said negative 8, negative 8, negative 8. He multiplied, which is true, right? Raising a power to a power, you multiplied those exponents. And so now 5 to the third is 125. So we don't leave this expression as 5 to the third because that doesn't look like scientific notation to have an exponent there where the 5 is. So we write it out. 125 times 10 to the negative 24th. And then is this scientific notation? No, so you'll have to take away how many decimal places?
2.
There we go, 1, 2, and we write the number as 1.25. You took away 2 place values, so you will have to add 2 back. Good. So times 10 to the negative 22nd. Thumbs up if you got that. Good. And number 46. I don't think it was Bianca. Anyway, check your answers. They should agree with this. Okay? And now, we're going to try this one problem together, and then you're on your way. So, the radius of a red blood cell A red blood cell, by the way, looks like that under a microscope. Well, no, you don't have to draw this. Or look at that. They look like little cinnamon candies here, it says. The most common type of blood cell in the human body. Red blood cells. It says they are biconcave. Do you see how they're dipped in the middle? Like a little lifesaver or something? Or like a certs? They have the task of carrying oxygen throughout your body. It says in women there are about 4 to 5 million red blood cells per microliter of blood, and about 5 to 6 million in men. People who live at higher altitudes have even more red blood cells because of the low oxygen levels in their environment. Isn't that interesting? Which is why sometimes elite athletes go train at high altitudes just to increase their red blood cell count legally. People like Lance Armstrong, that's doping. Taking your blood out, pulling out the red blood cells is what that group was found to have done. The United States Postal Service spike team. He won all those Tours de France, you know. And so they would take red blood cells and infuse them back in through an IV. So were they still working out and working hard at high altitudes and all of that? Yes. And then sheeting on top of it and putting red blood cells in their system so that more oxygen could be carried. When you're a long distance cyclist, you don't need to have huge muscles, you need endurance, and that's what these give you, you know? So if you're short on them, you end up feeling breathless when you just do something very small, like walking across a room. You might not be getting enough oxygen to your tissues. So really important piece of your life, these red blood cells. Look at the radius. The radius of a red blood cell is 4.5 times 10 to the negative 6 meter. Well, imagine, here's a meter stick. We don't measure red blood cells in meters, do we? If we did, that's what we would get, right? The radius of a mycoplasma bacteria is even smaller. 1.25 times 10 to the negative 8 meter. You need to take this down. Find the ratio of the radius of a red blood cell to the radius of the bacteria. And what does that ratio tell you? And then we'll find the ratio of the volumes of the red blood cell and the bacteria. What does that ratio tell you? Often when you face problems like this, just the unfamiliar scientific words make people want to stop, right? And really, you're being given little gifts right here. You don't have to go measure a red blood cell. They give it to you. It's just simply scientific notation. And you don't have to go measure a mycoplasma bacteria. They just give you the radius of it. So if we're asked to find the ratio, that's a simple math thing. A ratio of the red blood cell to the radius of the bacteria. So we could write that in words. We want the ratio of the red blood cells radius. The radius of the red blood cell to the radius of the little bacteria. So it's just a ratio, just is a little fraction, right? And so you can see how we're using some scientific notation to find it. Who can give us this ratio? What is the radius of the red blood cell? Bianca.
It's 4.5 times 10 to the negative 6.
Good. Okay. And now we simply need to find the radius of the little bacteria. What is it, Carly? It's given to you in the words up here.
1.25 times 10 to the 8.
Good. So they give it to you, and now what will we do? We're going to simplify this and write it in scientific notation. So 4.5 divided by 1.25. Anybody? Jimmy? Is it 4? Seems a little big, because 4 times 1 is 4, but 4 times the 0.25 would be another whole 1, right? That seems like it would be 5. So I think it's a little less than that. I think it's 3 point something. No, Anderson? Anyone else have that? 3.6? Okay, so we could write this as 3.6 times 10 to the Negative 6 divided by negative, do you see 10 to the negative 6 over 10 to the negative 8? So what is that? 10 to the negative 6 over 10 to the negative 8 is 10 to the second. So it would be 3.6 times 10 to the second red blood cells compared to 1 radius of a bacteria. We don't always show that denominator, but if we're asked about the ratio, we want to show a comparison of two numbers. Isn't that interesting? What is 3.6 times 10 to the second as a number? What is that number, Lauren? And 360. Move the decimal twice over, right? 360 red blood cells to 1 bacteria. That's a lot, isn't it? The radius of a little red blood cell is so small it's hard to imagine, but it is 360 times larger than this bacteria, which is ever so tiny. Okay? And then we're asked to find the ratio of their volumes. So what shape would you imagine these things are? I think this actually might be the bacteria picture, and that's the red blood cell. So what do you think they most closely resemble? Like a sphere?
Yes.
A ball, like a sphere? Okay, they're not all exactly the same. These are interesting. So if we use the radius and we think about volume, it says, let's find the ratio of their volume. Do you know how to find the volume of a sphere? We did this last year. V equals a ball. 4 over, what did we divide pyramids and cones by? 3, right? So 4 over 3, 4/3 times pi r. This is volume, so how many dimensions?
2.
Volume, 3 dimensions, so pi r cubed. So if we compare the volume of the red blood cell, imagining that it's approximately a sphere, we would have the volume of the red blood cell over the volume of the bacteria. This is just a little verbal model, right? I'm going to extend the board up. And so we could use this same formula for both. I hope you're taking this down. Because we could say 4/3 pi r cubed for the red blood cell, right? This is the red blood cell's radius over 4/3 pi r cubed. And this one's the bacteria. This is red blood cell, that's the bacteria. What happens to all these things, or what do you see could happen to the 4/3 and to the pi? Do you see? They can cancel. So we end up with 1 here and 1 here. So we're really just looking at the radius of the red blood cell cubed over the radius of the bacteria cubed. Do you have that down? And so they gave us the radius again. Here it is. We have 4.5 times 10 to the negative 6. There's our red blood cell. We're going to cube it and compare it to 1.25 times 10 to the negative 8. And raise that one to the third. Now, since they're both raised to the third, can we just cancel those exponents? No. Canceling those exponents is what operation?
It's squaring.
It would be, I guess you would be thinking you would be dividing, like something over something, right? But if we think about orders of operation, exponents happen before division, right? So we have to go find what these values are before we can do any division. So go do that. Okay, so having walked all the way through this, we see that a red blood cell's volume is 4.67 times 10 to the 8th compared to 1 volume of the bacteria, way bigger. We said there were 360 radius to 1 radius of a bacteria. But when we look at volume, look at how much huger this is. And Juliana, I don't know why this changed. This should ultimately be 6 plus 1 and 7 here, right? And so if we move that decimal, look at this as a real number, we have 4.67, right? 1, 2, 3, 4, 5, 6, 7. 46,700,000 times bigger. A bacteria You would have to have 46,700,000 bacteria to fit in one red blood cell. Isn't that amazing? Little devious bacterias. Those ones that invade you and you use antibiotics for? Look how small and devious they are. And what's interesting about them is that they can kind of live, even though they're not technically life, outside of the body for hundreds of years and then invade somebody later. Like they can go into suspended animation. So we can learn from them, because if we want to travel in space, we want to be able to suspend ourselves, right?